In the name of God, and I hope to be fine. In the previous session, we said about how we can update the error on the waiting links of the neural network. We said that using the gradient descent, we can do it. We considered the output error of neural network as a function, and then using the gradient descent we try to reach the minimum of this error, and finally we achieved this equation. Here EJ is related to the output of node G, and WIG is the weighting between node I and J, and OI is the related the output of the related to node I. And the sigmoid, as you know, is the activation function of each node. Okay, where I is the output of node I. And now in this video we want to calculate the updated weighting. We calculated the rate of this error with considering the weighting changes, and now we want to calculate the updating error, the updating weightings. By considering the learning rate that we called it alpha, we can say that new WJK is equal to the old WJK minus alpha multiplied by this fraction. Okay. Now we can set that we can set that differences between this WJK and the old WJK is equal to these sentences, this item. Okay, and then by this interpretation we can rewrite this equation in the form of matrix like this, and said that the differences between the new weight of 1 and the old W11 is equal to this. And as I said in this equation, we rewrite it sigmoid by S in the form of matrix, and K, and this K is related to the values from the next layer, and O is related to the output value from previous layer. It is directly rewrite by using the previous equation that I said. Okay, and then in the form of closed matrix equation, again we can rewrite in this form. Okay, that EK and this K is related to the next layer, and J is related to the previous layer alpha is the learning rate. Okay, and now we have one example to understand better this concept. Considering three layer, a neural network, input layer, output layer, hidden layer, and in each layer we have two nodes, and then we calculated the error of each node by this equation, target minus OK, and then after calculation we achieved that E1 is 0.8, E2 is 0.5, and then according to the previous concept, we can divide this E1 according to the weighting of W11 and W21, this error, and then after the usable equation, we can achieve that the error of this link is around 0.32, and then this is 0.48. Okay, and then E2 also divided according to W12 and W2. Okay, and then finally the summation of this error and this error, the link of W11 and W12. After the summation, the error 1 of this node is 0.42, and the summation the errors of these two links 0.48 and 0.4. The summation of this is this error, the error of this node. We said that we backpropagate the error to the previous layer, and then again we can divide this E1 to the previous layer. Okay. Then after that we have this equation, because we want to calculate the updated W. Okay, then E1 here is 0.8, and this term is the multiplying the weightings and outputs. Then for example, consider this. W11 multiplied by output, and see here, and the other one is this W21 multiplied by this. Then it is better that I write by this color, and then after that we calculate the summation of this multiplying. Okay, because these two link is fit to this node, the first node of the output layer. Then the outputs multiplied by this weight, this output multiplied by this weight. Okay. After that, this is the input of this node. We must pass this input through the sigmoid function, through the activation function. Here we also have this. Then after putting this value in this sigmoid function, the result is here, and then the next term, is 1 minus this sigmoid. Okay, then the middle term of this equation is here, and the output of first node is here. Okay, is this. Why? Because we said that this blue one is related to the next layer, and this is related to the previous layer. Because of this, there is 0.4, and this is also 0.8. We multiplied. Finally, we multiply this, and this, and multiply by minus. Then we calculate this fraction. Okay. And this is around this. And if you remember, we said that the new weighting is equal to the previous old weighting plus this updating rate. Okay, after we calculate this, we multiply it by learning rate, and according to the equation above, we said that new W is equal to old W minus alpha around the E divided by around the W. We calculate this, multiplied by this. Okay, here the learning rate is 0.1, and this minus is because of this equation. And then after the summation to the old W, W11 is this. Okay. And another thing, this is an example. Another thing, how we prepare data for the initializing the neural network. The inputs, if the value of the inputs are so large, then according to this activation function, to this segment, is around 1. And from the definite value, it is equal to this. This is saturation area of this segment function. And another thing, if we consider around 0, then it mapped, for example, if x here, then according to this it maps around ni. Okay, then this sigmoid function cause we have the smooth input according to this equation, and also the impulse is between 0 and 1. Then we normalize the x to this area. And for outputs, for the target and outputs, you also see that bigger than 1 and less than 0 is not good according to the activation functions. Then we considered between this area. Okay, and about the initial weights, again according to this definition, we considered between -1 to +1. Okay, and how we divide the weightings. For example, if we have 3 nodes, then we considered from this value to this. If we have 100, we consider from this to this. -1 divided by the root of 100 to this. Why? Because we want to have the summation of all weights was equal to 1. Because of this, we divided these weights to this range and distribute the initial weights according to the number of the nodes we considered and defined according to this equation. Okay. And then this discussion finally finished after a few sessions, and in the next part we want to learn Python. Thanks for your attention and your time. Have a good time.